Okay, we're rolling. So in Calc, you guys took Calc 1, right? And did you talk about something called the Fundamental Theorem of Calculus? Some people are nodding. Yes, you should have, right? That's. It sounds kind of important, huh? The Fundamental Theorem of Calculus. Okay, so it is. And you should have reached that at the end of, somewhere at the end of Calc 1. And this you should recognize this. And you most likely did some exercises using this, okay? In Calc 2, we're going to do lots and lots of study and problems regarding integrals, okay? So so we've got an equation here. Which side of the equation is an integral? You all should be thinking the left side, okay? So yeah, oops, what happened? Sorry. They're my beautiful kids. This is what I think I'm finally ready, sorry. Okay, integrals. So since much of the course is about integrals, and this is the fundamental theorem of calculus, we better know what this is about, okay? And my suspicion would be many of you in your class, you use this to do some exercises, but you never really learned what this was about, okay? So we're going to take a couple days, since the whole course is about integrals, we're going to take a couple days to really kind of explore what this fundamental theorem of calculus, this equation, is all about. And so that will, if you're familiar with this course, that's a little different. So like in this course, normally you just dive in and start solving integrals, okay? But we're just going to take a day and we'll be fine. There'll be some topics that aren't as important, and we'll just we won't do those. Just a few little things, and instead we'll take a day here or two to really understand what the fundamental theorem is all about. Okay, so we're making sense of this. Making sense of this integral expression equals, what is this, capital F of B minus F of A. Okay, so there's lots and lots of things going on behind the scenes here. The first principle is rate of change. Okay, so how does rate of change, what does it have to do with this? So let's just do a really easy example. So you're buying trail mix that costs $3.20 a pound, okay? And so you've put some in your bag, but you decide you want some more, okay? What additional cost will you pay for 1.45 more pounds of trail mix? So the first thing is, it's a very easy question to solve. So everyone solve that first. So what would you do and get an answer? What additional cost will you pay for 1.5 more pounds of trail mix? Everybody should be able to do this, okay? And that means you should be doing it, okay? You should be solving this little question. And if you're having trouble, I would suggest that you should rethink your major as an engineer, okay? And so can I have someone who thinks that they know how to do this, and a volunteer to tell me how am I going to find out how much am I going to pay for 1.5 more pounds of trail mix? I know that. Yes, sir.
It will be X, the original pounds plus 1.5 times 3.2.
But it says what additional costs will you pay for 1.5 more pounds?
It's 1.5 times 3.2.
He wants 1.5 times 3.2. Is that what you're going to say?
4.8.
Which is 4.8. Okay, right. So if it's $3.20 a pound, and you're gonna have an additional 1.5 pounds, then it's gonna be the right 3.320 times 1.5. Is that 480? That's the additional amount you're going to pay for an additional amount of 1.5 pounds. Okay, so this is a really simple example, but when things get more complicated, we need symbols. In calculus, we need symbols that represent this. So now we're gonna hold on to this. Just the answer, the numerical answer is important, and your thought process is important, but we need symbols that represent what's going on. So when it gets more complicated, like up above, then we have symbols to represent what's going on. So I want you to define each variable below completely and precisely and decide if it is unknown or known in the given situation above. Okay? So I've got 5 variables here. X, Y, delta Y, and K. So you're defining these as meanings, as statements in words. And then you're going to decide if we know the value of it or not in this original situation. Okay, so once you get a partner, and if you've never met your partner, then... Alright, I'll give you the first one to make sure you're on the right track. X is the total number of pounds of trail mix in your bag. Total number of pounds of trail mix in your bag. Okay, keep going. Keep going. Okay, what about Y? Somebody new. What do we think? What's that? Final price. Is it dollars?
Yeah.
Yeah. So the cost of X pounds of mix in dollars, right? So Y is your cost. So then so do we know either of those values of X or Y in this situation?
No.
Why not? Who said no? Someone said no.
Why is 4.8?
What? Do we know what X or Y is in this situation?
No.
I think we know.
Yes, we do.
Some people are saying yes, some people are saying no.
X is unknown.
Why is X unknown? Who said X is unknown? Why?
Because we don't know the total amount of pounds that we have.
Right, we don't know the X, we don't know the total number of pounds of mix in our bag. We just know we had some amounts and then we added some more. Okay? And we don't know the total in the bag. So what about Y? Do we know Y? No, don't know Y. Alright, what about delta X?
Yes.
What is it, first of all? What is delta X? How do we define what that is? It's really important here. Hopefully you had some exposure to that in Calc 1. Yeah?
The change in X.
Okay, so if it's the change in X, what would it be here? If it's the change in X, then what does that mean, the change in what?
It's the 1.5 pounds and we add.
Okay, so she's saying it's the 1.5. It's the additional number of the change in the number of pounds. Okay? And what is delta Y?
Changing the price.
Change in the price. So We do know delta x. Delta x is what? Do we know delta y?
Yes.
Well, it's not given, but we found it, right? What was it? 480. Okay, and then what is this thing I'm calling k? Anybody figure that out?
3.2.
Yeah.
It's the constant, it's $3.20 per pound.
Okay, and so that's our constant rate of change. I forgot to change it, sorry. It's from our previous slide. So what was it? $3.20? Okay, so now we've got all these things defined in this situation. X, Y, delta y, and k is our rate of change. So using the symbols now, write an expression that computes the answer to the question of both. So write an expression using the appropriate variables. You're not going to use all of them, but you can use some of them to write an expression that computes the answer to the question of both. Can you do it? Did you get it? No, not yet. How did we compute the answer? So the very first thing we did is we computed the answer. What did we say? We said that, what? To get the answer before we did any of this variable stuff. What did we do?
We took 4.8 plus the initial one.
4.8 plus the initial one. No, we didn't do that. What did we do to answer this question? What additional cost will you pay?
1.5 times.
There you go. 1.5 times 3.2.
Mm-hmm.
And what was our 1.5? That was symbolized by?
Delta x.
Oh, yeah, so that one. Delta x, okay? Times k. And what does that give us? So that very natural thing you did at the beginning where you took 320 times 1.5 to get $4.80 additional cost for 1.5 additional pounds can be summarized like this, right here. Or delta y equals k delta x, where k is what again? K is the rate, right? Rate of change. The rate of change here is $3.20 per pound. So this is our kind of our bedrock relationship that uses constant rate of change. If we knew a change in this independent quantity, then we're just going to take k times that to get the change in the dependent quantity. In this case, we have 1.5 pounds. We're going to multiply that by $3.20 per pound. Gives us the $4.80 additional cost. So let's do it again here. Next, we're going to remove 0.4 pounds from your bag. Return it to the bin. To find delta x, delta y, and k. And answer the question. So you can do it with your partner. Okay, what's the meaning of delta x? Back here in the back. Right, Epic. So what does delta x mean? What's this meaning?
It's k times the delta.
Note the meaning of that. Like,
I mean, the difference between the
difference between the x's, but in terms of the trail mix scenario. So what, if we're talking about the pounds and the dollars and all that stuff, what is delta x in terms of what's going on here?
change.
The change of?
X.
Okay, but I'm going to talk about the situation, the change in?
In the bag.
The change in the bag.
Like the change from putting, moving some pounds from the.
Okay, so it's change in the number of pounds in the bag. Do we know it? 0.4.
Isn't it negative?
Isn't it negative? Is it 0.4 or negative 0.4? Negative. Negative. Decrease. Decrease. A negative change is a decrease. Okay? What is y? Somebody knew.
0.4 times.
No. What's the meaning of it? Meaning. What are we defining it as? Change in cost. In dollars. Okay? What's K? That's our constant rate of change. Do we know that? Positive or negative? Positive. If you, yeah, so, right, if. So now, how can we compute what delta y is? If we remove 0.4 pounds, or delta x is negative 0.4, and our constant rate is 3.2, then delta y equals? And how'd you get that?
Times delta.
Right, 3.2. We're going to take the 3.2 dollars per pound times negative 0.4. Or, in other words, K delta x. That's the key here. So something that should feel very natural, that you're taking 3.2 times the negative 0.4, we need symbols to represent that. And so that's the same thing as delta y equals K delta x. If you go 3 hours at 60 miles per hour, how far do you go? It's another question. So if you travel for 3 hours at 60 miles per hour, how far do you go? 180 miles. That's the same. That's another example of this as well. 3 hours, 60 miles per hour, 180 miles traveled in those 3 hours. Okay. All right, another example. So a soldier lowers the American flag from the top of the pole at 0.75 meters per second. How much does the height change from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? Okay, so I'm going to give you y here. Y is defined as the height of the flag in meters. Define each variable below completely precisely and state the value in the situation if known. So I'm giving you y. Y is the height of the flag in meters. Work together. You can talk. Work with your partner. So there's some other things. What specific amount of time is x? Yeah.
Seconds since the flag
Left the top. Right. Seconds since the flag left the top. Very good. Okay. So x is number of seconds since the flag left the top. And I told you what y was. So what is delta x? How would you define it? Right here in the green shirt. How do you define delta x?
Delta x is that change in time.
Change in time. In seconds. And delta y then? Change in height. Okay. So what is K?
Speed. Zero constant.
Okay, I heard speed, I heard the constant, and what is its value?
Negative 0.75.
What's that?
Negative 0.75.
He wants negative 0.75. Is it negative or positive? If y is height, then the rate of change, if the flag's coming down, then the rate of change has to be negative. Did you get that? How many people got that when you're working with your partner? Okay, that's important because so K is negative because how y is defined. Y is defined as how high up it is. So if it's coming down at that rate, it's going in the negative direction of y. So that rate of change has to be negative 0.75. Okay, which of these do we know? Do we know x or y in this given situation? Do we know delta x? What is it? 2.4 minus 0.6. Is that right? Is that 1.8 seconds? Okay, and so then change in height. So if it's going down, it's 0.75 meters per second for 1.8 seconds, then you would simply do what? We would just multiply, right? You just take the 0.75 times the 1.8, but we know that's negative. And what do you get for that? 3.5?
1.35.
3.5 meters? Okay, and so again, what are we saying there? This principle here now, K is negative. So when K is negative and we have a positive change in time, then our change in height will be negative, and that makes sense because the change in height it's going to be lower. Later in time, it will be lower, so we get a negative change in height. Okay, so this is just putting symbolism on a very simple concept, but the symbolism is really important when it gets more complicated. Okay, anybody have a question on this? Let's think about this flag lowering situation. In this left graph here, what am I showing you in this left graph? What am I showing by this blue line here?
Constant.
The rate at which the flag.
Yeah, what was that rate of change in that flag example? Negative 0.75. So I'm showing you as time goes by, that rate stays constant, right? Okay, so is it realistic? Is it realistic? No. The flag's coming down in a steady state because pulling the rope? No. So maybe something more realistic would be like this. So what's happening? So talk to your partner. Make sense of that graph. Can you make sense of that? That's a rate of change graph. Maybe more realistic for the lowering of the flag. Can you make sense of it? Go. Why might that be more realistic? Okay, so here's the more realistic graph for lowering the American flag. How much does the height change from 0.6 to 2.4 seconds since the flag left the top of the pole? 1.8?
Times the rate.
1.8 times the rate? What's the rate?
Well, it's different depending on what time you're at.
Okay, go ahead and solve it. So answer this question now. With this rate of change profile or graph, for this as time goes by, how much does the height change from 0.6 to 2.4 seconds?
negative 1.35.
You want the same answer? The same answer? So it's delta y equals k delta x. So delta y equals k is our negative 0.75 times 1.8 seconds. Do you agree? Is that right? So I'm nodding. Everyone agree? No?
No.
Why not?
Course, when he decreases his speed, so sometimes the rate is 0.
Yeah.
And at that moment, if the time passes and the dot y should not be constant.
Right. Is the rate of change negative 0.75 over this time period from 0.6 to 2.4 seconds?
It's not constant anymore.
It's not constant anymore. Most of the time it is, but there are these gaps of time that are significant that the rate is not negative 0.75. It's slowing down to 0 and speeding up to the negative 0.75. So is this right? No, this is not right. Because we don't have a constant rate of change. In those other two examples with the trail mix and when we did this originally, it was a constant rate, and so we could easily do k delta x and we'd be done. Go on to the next problem, right? But this is a kind of more realistic situation where the rate is changing, so we can't just do k delta x because that k is changing. Do you see it? That k is changing. So instead of k, instead of a constant k, so no longer do we have constant rate of change k. Instead, this is principle 2, we have a changing rate of change. Changing rate, if you notice that. So, and that just throws a big wrench in this, okay? We were cruising along and now we come to a grinding halt in making progress here. Because if we're going to use this k delta x, we have to have a constant rate of change for that to work. Okay, so it's like instead of k, a constant, it's like a rate function. So we could call it f if we want. F of x, a rate function that tells us different rates of change at different times x since the flag started to be lowered. And it just, like we said, we hit a wall here. We hit a wall. So but we still want to know. We still want to know in this time period how much does the flag go down? Is it going to be more based on this rate? Is it going to be rate function? Is it going to be more or less than negative 1.35 meters? Is it going to make it down further than negative 1.35, or a lesser amount than 1.35?
Less.
He wants less. Why?
Because there's points where it doesn't go down at all.
Right. So the rate kind of for each pull is negative 7.5, but in between pulls, it's like slows down to 0 for an instant and then heads back to the lower rate. So, or to the kind of the base rate. But in here, the flag is traveling what? Slower or faster down? It's traveling down slower. So it's not going to make it, our answer is going to be a number less negative than 1.35. Maybe negative 1.2 or 1.15 or something like that. We don't know. But because there's these moments of time when it's traveling down slower, it's not maintaining that negative 0.75 for the whole time. So what do we do? So this next part is what you should have learned in the first calculus course. Did anyone learn how do we attack this problem? How do we figure out how far it went down with this changing rate from 0.6 to 2.4 seconds?
We take 2 points.
What's that?
We take 2 points.
Take 2 points? What 2 points?
Same time.
2 times intervals.
What's that?
I take like 0.4 and 0.5
Okay.
and find the change there.
Okay. So you're talking about breaking it into a smaller interval. Look at a smaller interval of time. So if we took this, so we've got this time period from what? From 0.6 to 2.4. There's that time frame that we're looking at. And we want to try to figure out what the true. So here's delta what? Delta x or delta y? That's what we called delta x before. But so now what we're going to do is take that time frame and we're going to break it up into chunks, small chunks. So that's 1.8 seconds, is that right? So let's not make it too hard on ourselves. Let's do, how about, I don't know, so let's do chunks of 0.3 seconds. So from 0.6 to 0.9, from 0.9 to 1.2, 1.2 to 1.5, 1.5 to 1.8, 1.8 to 2.1. And now we'll call these chunks delta x. So we're going to call delta x equal to 0.3 seconds. Why do we want to do that? So the whole interval is no longer delta x. Now our literal intervals are going to be each delta x of 0.3 seconds. How's that going to help? What's that going to do?
We can find the graph under the line.
Okay.
And check it.
So we're going to look in each interval and do what? What are we going to do in each interval? What's that?
Find the rate of change in each interval.
Yeah, so is there just one rate of change in each interval? No, okay. So here's what we're going to do. We want to use this principle of k delta x, but that requires what? Constant rate of change. So if we could get a constant rate in each interval that kind of pretends to be this changing rate function, then we can make an estimate. Do you see? This is what they should have taught you. So in this, what about this interval here, from 0.6 to 0.9? What would be a good pretend rate?
0.75.
Yeah, I mean, it's pretty much 0.75 for that whole thing right there. Okay, so that's done. From 0.9 to 1.2. What would be, what constant rate could we pretend is happening to kind of, or what constant rate could we assume that kind of pretends to be what's actually happening in that interval? So if we're going from here to here, anybody have a suggestion? I mean, do we want the constant rate to be negative 0.75 again? No. Do we want it to be 0?
So the half of it.
Halfway between, like it kind of looks like it's going from negative 0.75 to 0 in that thing. So what about halfway between? So for that interval right there, if we just take, was that negative 0.375? We're making a pretend function here. We're going to pretend that it, instead of going from negative 0.75 to 0, it's constant at negative 0.375 for the whole time interval. Does that make sense? And then what about the next one? Same thing. Because here it goes from 0 to negative 0.75, so let's just go ahead and assume it's that again. This isn't exact science. We're just trying to come up with something. All right, what about the next one? Down here again. And what about from here to here? Is it halfway between again? No, from here to here it's less. It's closer to 0. So maybe we want to do let's do a quarter. Maybe a quarter of 0.75, so like up here, to pretend what's going on there. And then the last one, we can do negative 0.75 again. So what I've drawn in blue is a rate function that's pretending to be the changing rate function. It's trying to be like it, but it's all based on constant rates. So what can we do? We can still use the delta y equals k delta x. Do you see? So now based on these that we picked, what do we say? So we said these were negative 0.75. And then we said this was negative 0.375. Those two. And then this one, we just said, what, negative 7.5 over 4. Just split it in half again. Again, this isn't exact science. We're just trying to come up with something to get started. Get started on what would the true change in the height of the flag be? What do we have to use? We have delta y equals k delta x, which depends on a constant rate. So let's turn our changing rate function into a bunch of constant rates so we can do it. So now, can you can you find, based on our approximation or pretend rate function, can you find how much did the height change? Do it, work with your partner. Figure out how much did the height change based on our blue pretend rate of change function, trying to be like the red real rate of change function. All right, I'll walk around if you're stuck. Okay, let's have somebody new explain how you approach this. How about right here? Did you make progress on this? Right here. Right, so she wants to find the delta y for each section and add them together. So how did you find the delta y for the first section? What'd you do?
Going there to change fundamental x.
Hey, so tell me what that is, yeah.
Minus 0.75
Okay.
times 0.3.
Yeah, so she's doing like the first, so we call it K1 delta x. And so negative 0.75 times, what was it?
0.3.
And that gives us the change in that first 0.3 seconds. And then keep going, yeah.
And then plus minus 0.375
Okay.
times 0.3.
Right, and so that'd be like K2 delta x again. So the minus 0.375 times 0.3. This is what you should have done. So now we can use that K delta x, but we have to use it on each interval and then add them up, add all the changes up. So then I think we get that one again, right?
We can take delta x out.
Yeah, you can, but then you kind of lose the idea of K delta x. Yes, you absolutely can. Delta x is the same for them all, so you could factor it out. But we really want to focus on what the meaning is that we're finding one delta y at a time and we're adding them all up. So I prefer if you don't factor it out, but just, yes, you can. You get the same number if you do. Okay, so then we're going to go all the way here, until, what's the last one? How many rates do we have?
4.
4? 6, right? 6 intervals. So this is our idea here, that we're going to sum up K1 delta x plus K2 delta x plus all the way up to K6 delta x. And so I'm not going to write the whole thing out, but let's just do the last, write the last two down. So this number, this fifth one, what was this fifth one? Negative what?
Negative 1.9. 1875.
1875?
Yeah.
Can you still read that tiny writing? 0.3, and then the last one? Another, just a normal one, right? Negative 0.75 times 0.3. And let's make sure we all got the same answer. What do we get? And we're expecting this to be a bigger negative number than 1.8 or a smaller negative than 1.8? Smaller negative, because there's these time periods where the flag is traveling slower, where he's changing hands, right? It's changing hands, so it like it pauses for a moment each time. So negative what? 1.18125. 18125? Someone else get that?
I got negative 0.95625.
Yeah,
Negative 0.9?
yeah, 0.926.
Sorry, I think you've been overruled. Whoever said that first number. Sorry. Are we in agreement? Negative 0.9 what?
95625.
996. I'll just round to 996. And what's the units on that?
Meter per second.
Meters per second. Agree? What are we calculating? Change in height. Delta y, change in height. So it's just meters. Is it exactly right?
It's negative 0.956.
Not 9, it's 9.5.
956? Thank you. Okay, is it exact? Is this an exact result?
No, it wasn't estimated.
Yeah, we know we had to figure out some kind of estimated rate function with these constant rates. So it's not going to be an exact number. It's not going to be exact, but it's a start, right? It's a start. Okay, so then what could we do to get a better approximation?
Make delta x smaller.
Next one.
All right, what would the effect of a smaller delta x be that would result in us getting a better approximation? Why make delta x smaller? What would that do that would give us a better approximation?
More accuracy.
Okay, why? Why is it more accurate? What happens?
Taking more area.
What's
more
that?
Counts, taking more area.
Okay, so I'm glad you said that. How many people were thinking about area when you did this problem? Okay, so notice I didn't make any rectangles. We didn't do any area. Okay, because really, what does time and height of a flag have to do with area? It doesn't have anything to do with area.
Diameter of the graph.
Okay, right. So it's been beaten into you that you're finding area. But no, we're finding height, change in height. We're finding change in height. That has nothing to do with area. So notice I didn't make any rectangles. What we're really doing, we're not making rectangles. We're making a new rate function. And a new rate function wouldn't have any vertical lines on it. Okay? It would just be, our rate function would just be these horizontal constant rates that are trying to be like our actual rate function. It wouldn't have any vertical lines, and you wouldn't calculate any areas. Okay? Area is just kind of a coincidence that it works out that because we're doing it in rectangular coordinates. It just happens that this also makes the area of rectangles. But the problem has nothing to do with area. It has nothing to do with rectangles. It has to do with a flag coming down and how far did the flag come down. Okay, so I know that every book and many teachers are telling you that this is about area, and I want to try to change your mind. It's not. It's about rate of change. It's about trying to make this rate of change function, trying to pretend that it's a constant rate function, and using this principle of k delta x to get little changes and add them all up. Okay, so back to my question. Making the changes in x smaller, why will that achieve a better result? What will happen? Why will it achieve a better result? Yeah.
It will give us more rates.
More rates, okay.
So it will be more accurate.
Okay, we're getting onto it now. So
We have more constant lines.
Okay.
That will give us more constant numbers.
So yeah, we'll have more constant rates, but then again, what's the link then to more accuracy?
Less arrows.
What's that?
Less arrows.
Less errors. Why are there less errors? So we get more constant rates. Yeah.
There's more precision to the rates of change as you get smaller and smaller.
Precision to what?
So the real number, because
Yeah.
you know the real change rate, which is a negative 0.75.
Right. So when we use more rates, those in smaller intervals, the constant rates they'll do a better job matching the rate function. So are we doing a very good job matching the rate function with ours? No. Okay. It's like chunk, 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 right? So if we had smaller intervals, those constant rates they'd mimic the graph better. They'd hover, they'd hang, they would reproduce the graph better. And the smaller you make it, the better. And I'll show you a demonstration tomorrow of that. I got some cool animations that'll show you what happens when you make delta x smaller and you have more constant rates. They match the real rate function better and better and better as you make the change in x smaller. Okay, but we're just going to stick with this principle for now. And we'll just make this part of the homework here, and you can get started on it. There's another situation. You can get started here in class. Let's just go till 6 today. So you're working on it for 10 minutes, and then it'll be. This is a rate. I'm giving you a rate of change graph, just like in the flag example. I gave you a rate of change graph. So let's find that. Where is it? There it is. Okay, so let's start by interpreting this point right here. 0.4, 30. What does that point on the graph mean in the situation about the insects? What is that telling us about the insects? Just that 1 point, 0.430. What does it tell us?
Decreased by half.
What's that?
Is it decreased by half? Like carry over to.
I don't see anything about a half. I'm just looking at this one point. 0.4, comma 30. Can we interpret that point? This is really important. Can we interpret that point on the graph? What does it mean? What's the point mean?
It's a constant.
What's that?
The constant.
The constant. 0.4, comma 30. What does it mean?
After 0.4 months,
After 0.4 months, let's write this out. Everyone write this out. After 0.4 months,
the insect population is changing at 30.
the insect population is
Changing at 30 insects per month.
changing at, it's a rate of change. So these y values here, y values on this graph are they population or population per month?
Population per month.
Yeah, insects per month. This is a rate of change graph. So your y values, just like the flag the graph I showed you, these are rates of change. So at 0.4 months, the insect population is 30 insects per month, or is changing at. That's what that point tells us. That's a skill that you need to have when you look at a point on a graph. Interpret that point, right? It's two quantities, corresponding values of two quantities taken together. So at 0.4 months, the insect population is changing at 30 insects per month. So tell me about the insect population at that moment, at 0.4 months. What can you tell me?
It's increasing.
He wants increasing. Is it increasing or decreasing? The insect population. You have a rate of change of positive or negative 30. Positive 30 is your rate of change. So is the population increasing or decreasing? In or D? In. In. Because your rate of change is positive. Right? In the flag example, all the rates of change were negative, which meant that the flag was coming down the whole way, right? It was coming down. Here, the rate of change is at 0.4 seconds. It's positive 30, meaning at 0.4 seconds, the insect population is going up 30 insects per month. Going up. Do you see it? Your y values on this graph are rates of change. They're not amounts of population. So that should help you determine then what's happening between 0.2 and what did you say, 0.6? What's happening to the population from 0.2 to 0.6?
The rate of change.
I'm asking about the population, not the rate of change. Given the population, given the rate of change graph, what's happening to the insect population? Increasing or decreasing? Increasing. It's just the rate is slowing down of increase, right? The rate of increase is the highest at the beginning, whatever that number is, 60 or whatever that is. And then at 0.6 seconds, the rate of increase, it's still a rate of increase though, because it's a positive rate. It's just a slower rate of increase. But so over that time period, that population of insects is increasing through there. Even though the rate is slowing down, the rate of increase is slowing down. Does that make sense? That's important, okay? All right, so now I think you have a fighting chance at number 2. And